And welcome to the third session of this exciting short course on choice modeling given by Professor Topaloglu from Cornell. I also want to quickly remind you that on Wednesday, it's a standard seminar-like, and hopefully you have enough backgrounds to follow that if you didn't have background in choice modeling, given by Professor Vulcano, same time on, I believe, personalized promotions that will build on obviously choice models technique and technology. All right, Huseyin, the floors are yours. Thank you.
Thank you. Sharing my screen. Okay. Thank you everybody for making the time and for being here. So today is going to be our third and last lecture. And today we're going to be talking about dynamic assortment optimization. So what is dynamic assortment optimization? How does it differ from the assortment optimization problems that we talked about in the first two lectures? So in the dynamic assortment optimization setting, the firm is going to have access to a whole bunch of products, but these products are going to have limited inventories. And we're going to be selling these products over a finite selling horizon. So the customers are going to arrive over time, one by one. And for each arriving customer, the firm is going to look at what inventories I got left. And the firm is going to look at how much time do I left to sell these inventories. Based on that, to each arriving customer, the firm is going to offer an assortment of products. And the customers are going to choose within the offered assortment of products according to a certain choice model. And the goal of the firm is to figure out which assortment of products to offer to each individual arriving customer as a function of the remaining inventories of the products and also as a function of the remaining time in the selling horizon, so that it maximizes the total expected revenue collected over the selling horizon. So this is what I mean by a dynamic assortment optimization problem. Now we're going to be selling finite inventories of products over a finite selling horizon, and our assortment decisions that we can make for successive customers are going to be limited by the availabilities of the inventories. So that's what we're going to be talking about today. So here's an outline. First, we're going to formulate this dynamic assortment optimization problem as a dynamic program, but that dynamic program is going to be high dimensional, so we're not going to be able to solve that dynamic program computationally in a tractable fashion. So now we're going to turn our attention to these policies called the bid price policies. What do I mean by a bid price policy? In the bid price policy, for each product, we're going to associate a bid price, and the bid price is going to characterize the value of a unit of each. The bid price is going to characterize the value of each unit of inventory for that product. Okay, for each product, we're going to associate a bid price, and the bid price for that product is going to characterize the value of a unit of product. So then, when I sell a unit of product, I'm going to make a revenue. That's the revenue of the product, but I'm going to lose a unit of the inventory for that product, and there's a value associated with that, which is the bid price. So now, whenever I sell a product, the net revenue I'm going to obtain is going to be the revenue of the product minus its bid price. So in our bid price policies, we're going to find assortments of products to offer to our customers that maximizes the net expected revenue from a customer. And by net expected revenue, I mean the revenue of the product minus its bid price. So that's going to be the class of policies we're going to be looking at. And the first thing we're going to do is we're going to look at a simple deterministic LP formulation that allows us to extract bid prices out of that, that allows us to extract bid prices from that deterministic linear programming formulation. So the first, we're going to formulate an LP to come up with bid prices. But it turns out that we're not going to be able to prove anything about the bid price policy that comes from the linear programming formulation. After that, I'm going to show you another idea to compute bid prices that gives us a half approximation guarantee that is guaranteed to obtain half of the optimal total expected revenue. In those bid prices, we're going to make this important realization. Bid price is the value of a unit of inventory for a product. Bid price characterizing the value of unit of inventory for a product, it should depend on how much time there is left until the end of the selling horizon. If I have a lot of time left until the end of the selling horizon, I should be able to grab a lot of value from that inventory. If I don't have that much time left until the end of the selling horizon, I shouldn't be able to extract that much time from the unit of inventory. So then our half approximate policy is going to be based on coming out with time-dependent bid price. And I'm going to give you an algorithm to compute time-dependent bid prices. And then after that, I'm going to show you another half approximate policy. And this half approximate policy is going to be based on not only constructing time-dependent bid prices, but also on capacity-dependent bid prices. And the motivation is going to be over there will be the bid price of a unit of inventory, the value of unit of inventory should depend on how much capacity I have. Namely, if I have 100 units of capacity, then the marginal value of an additional unit of product is going to be different versus when I have 10 units of capacity, and then the marginal value of an additional product is going to be different. So then we're going to construct not only time-dependent bid prices, but also capacity-dependent bid prices, and that is going to give us yet another half approximate policy. And now we're going to look at some experiments that compares the power performance of these time and capacity dependent bid prices. Okay, so this is the outline for today. So we're going to focus our attention to bid price policies, which is based on associating a value for each unit of inventory for each product. Then the class of bid prices basically is going to find an assortment that maximizes the expected net revenue from each customer. And the net revenue of a product is revenue minus its bid price. And then the first thing we're going to do is we're going to look at an LP formulation to extract bid prices. And then we're going to do something more sophisticated. We're going to come out with an algorithm that computes time-dependent bid prices. The pulse that we get from those bid prices is going to be half approximate. And then we're going to go even more sophisticated. We're going to compute time and capacity-dependent bid prices. And then we're going to get another half approximate policy out of those time and capacity-dependent bid prices. Okay, so let's get started. The first thing we're going to do is we're going to write a dynamic program for our dynamic assortment optimization problem. And then we're going to use an LP to extract a bid price policy. So here's the problem setting. So we have a whole bunch of products. Each one of these boxes is a different product, and we have the no purchase option. So now each one of these products have a limited amount of inventory. So each one of these squares that's replicating product is the inventory of each product. So then when customers come into the system, we're going to look at how much inventory we got for each one of these products. And we're also going to look at how much time we have left for selling these products. And based on those two pieces of information, we're going to figure out which assortment of products to offer to the arriving customer. And the customer is going to look at the offered assortment, and she's going to make a purchase within the offered assortment or leave the system without purchasing anything. And the choice of the customer is going to be governed by a discrete choice model. And the goal is, again, to find a policy to decide which assortment of products to offer to each arriving customer as a function of the remaining inventories and as a function of time, so that we maximize the total expected revenue over a finite selling horizon. So this is what we mean by dynamic assortment optimization. So now I have some applications for these kinds of problems. One is online retail on the left. The other one is revenue management problems over parallel flight legs. Let me try to unpack these kinds of two applications for you. So let's talk about online retail. Let's say that we go on to Amazon and say we would like to purchase noise canceling headphones. Amazon has a whole bunch of noise canceling headphones that it can offer to us. And each one of these models of noise canceling headphones has a certain amount of inventory available in the warehouse. Right? So then, based on the inventory availability of these headphones, and based on maybe when the next replenishment is going to happen, based on maybe the amount of time that Amazon has to sell these products, Amazon is going to figure out which assortment of noise canceling headphones to offer to us. And looking at this assortment, we're either going to make a purchase within this assortment or decide to leave the system without purchasing anything. So these kinds of dynamic assortment optimization problems happen a lot in online retail. Another application area we can look at is revenue management on parallel flight legs. So let's look at a whole bunch of flights that is being operated by a particular airline between a particular origin and destination pair. Let's say we're looking at a bunch of flights that's operated on a particular day between New York City and Boston. So this airline offering a morning flight, a late morning flight, an afternoon flight, and an evening flight. These are single flight legs. And each one of these flights have limited capacities on that. So whenever a person comes onto the airline's web portal and says, I would like to go from Boston to New York City to Boston on this particular departure day, based on the remaining capacities on these flights, and based on how much time there is left until the departure time of these flight legs, the airline is going to figure out which assortments of these flights to offer to the customer, and the customer is going to look at what is offered, and she's either going to make a purchase within the offered assortment or decide to leave the system without purchasing anything. So these are the kinds of applications we have on mind.
Just a quick question. In particular with respect to the second application, but also on the first one, the different products might have different horizon, right? Here the assumption is that all of them have the same.
We're going to look at the setting where all the products are going to, so we have a finite selling horizon. At the end of the selling horizon, game is over, and that's going to be the selling horizon for everybody. So we're going to have a finite selling horizon.
Right. And so the complexity there becomes much I mean,
yeah, I don't want to go to the case where we think about different products are being replenished by different periodicities. That makes things a lot complicated. And this for policy or this story of having a finite sailing horizon over here, it's a perfect story because I'm looking at all of these flight legs that are departing on the same day. So now they have the departure date, and the story over there is perfect. And online retail, the story seems a little bit of a stretch, admittedly. Good. So the first thing we're going to do is we're going to try to formulate this dynamic assortment optimization problem as a dynamic program. But again, it's going to turn out to be a high-dimensional dynamic program you won't be able to solve. Then we're immediately going to start looking at approximate policies. Okay, so here's some notation. N is going to be the set of products that we have access to. T is going to be the set of time periods in the selling horizon. Namely, we're going to have a finite selling horizon. We're going to take that selling horizon and chop it into little time periods. And these time periods are going to be small enough that there is going to be one customer arrival in each time period. And T is going to be the set of time periods in our selling horizon. CI is the initial inventory available for product I. So CI is the initial capacity for product I. RA is going to be the revenue for product I. Again, this is how much money we make if we sell one into a product I. And this PIT of S is going to be the choice probabilities as a function of the assortments of products that we offer. Namely, PIT of S is the choice probability of product I, given that we offer subset S of products at time period T. Once again, PIT of S is the choice probability of product I, given that we offer the assortment S, subset S of products at time period T. And lastly, we're going to formulate a dynamic program. To use as a state variable in our dynamic program, I'm going to use XI. XI is going to be the remaining inventory for product I at the beginning of a generic time period. So let's write our dynamic program. We're sitting at time period T. The remaining inventories of the products is given by this vector of Xi. So this X is a high dimensional vector. Component I is keeping track of the remaining inventory for product I. And I'm computing the total expected revenue to come starting from time period T with the inventory vector X. If I offer the assortment S of products, this is the probability that the customer arriving at time period T purchases product I. If she purchases product I, we're making a revenue of Ri. And now we're going to walk into the next time period with one less unit of capacity for product I. EI is the ith unit vector. If I offer the assortment S, this is the probability that the customer doesn't purchase anything. And now we're going to walk into the next time period with the same amount of capacity that we had before. So this is the immediate expected revenue. This is the expected value function at the next time period. I'm choosing an assortment that maximizes that immediate expected revenue and the expected value function at the next time period. And the assortment that I choose has to be a subset of the products for which I have inventories. So N of X is the set of products for which I have inventories, given that my inventory vector is X. Okay, so an X is the set of all products with positive inventories, given that my current inventory vector is X. So this is the dynamic programming formulation of the problem. Let me try to mold this. This is the dynamic programming formulation of the problem. And this is the dynamic program that we cannot solve. And the reason for that is this state variable is a high dimensional vector. So we cannot evaluate and store all of these value functions for every possible value of the state. Okay, for every possible value of the vector X. So then the first thing we're going to do is we're going to formulate a simple deterministic linear program. And hopefully out of this deterministic linear program, we're going to extract some kind of a policy. And here's what this linear program is going to look like. In this linear program, our decision variable is going to be ZT of S. And I'm going to interpret this decision variable ZT of S is the probability that we offer subset S of products at time period T. Okay, so my decision variable ZT of S is the probability of offering assortment S of products at time period T. So let's start with the objective function. At time period T, if I offer the subset S of products, this is the probability that an arriving customer is going to purchase product I. If the customer purchases product I, we make a revenue of Ri at overall products. So this is the expected revenue that we obtain if you offer the subset S of products at time period T. This is the probability that we offer the subset S of products at overall assortments. This is the total expected revenue that we obtain at time period T. At overall time periods, this is the total expected revenue over all time periods that I'm trying to maximize in the objective function. This constraint that we have here is a capacity constraint. Let me again start with the left-hand side. At time period T, if you offer the subset S of products, an arriving customer is going to purchase product I with this probability, PIT of S. And this is the probability that we actually offer the assortment SO products at time period T at overall assortments. So this is the expected number of sales for product I at time period T. If you offer the assortment S, this is the probability that a customer arriving at time T is going to purchase product I. This is the probability that I actually offer assortment S at overall assortments. This is the expected number of sales for product I at time period T. At overall time periods, this is the total expected number of sales for product I over the whole selling horizon. And I'm saying that the total expected sales for product I over the whole selling horizon is not going to exceed the capacity for product I, initial capacity for product I. So this is a capacity constraint written in the expected sense. And this last constraint says at every time period, the total probability with which we offer an assortment has to be equal to 1. At every time period, we have to offer some assortment, but the assortment that we offer could be an empty set. Okay, so this is a deterministic linear programming formulation that is formulated for this dynamic assortment optimization problem. And it's a deterministic linear programming formulation that is formulated under the assumption that the purchases of the customers are going to take on their expected values. So I'm writing the capacity constraint in the expected sense here. Okay. So then out of this linear program, how do I extract a policy? Out of this linear program, how do people extract a policy? They do the following. They solve this linear program. Instead of using the primal optimal solution, they use the dual optimal solution to this linear program. In particular, let mu I star be the optimal values of the dual variables associated with the capacity availability constraint for product I. So this mu I is the optimal value of the dual variable associated with the capacity availability constraint for product I. What is that mu I saying? Mu I is telling me if you increase the capacity for product I by 1 unit, how much more revenue you would have made. So mu I is essentially characterizing the value of 1 more unit of capacity for product I. And in revenue management vocabulary, those mu I's are called bid prices. So I'm going to call mu I as the bid price of product I. And again, mu I is the value of additional unit of capacity for product I. Mu I is the value of 1 unit of capacity for product I. And again, I'm grabbing those bid prices from the optimal dual variables for the capacity constraint for product I. So now by characterizing these mu I, by using these mu I's to characterize the value of 1 unit of product I, here's how we construct a policy that's coming out of this linear program. Let's say we're sitting at time period T, and the remaining capacities on our products is given by this vector X. So then according to my heuristic policy, I make my decisions as follows. If I sell 1 unit of product I, this is the revenue that I'm going to make. That's the revenue of product I. But if I also sell 1 unit of product I, I'm going to lose 1 unit of product I, and there's a value associated with it. And that value is mu I. That's the bid price of product I. So then this difference is the net revenue contribution from product I. Revenue minus the value of the unit that I just lost. And at time period T, if I offer the assortment S, this is the probability that a customer purchases product I. At overall products, so this is the net expected revenue that I obtain if I offer the assortment S at time period T. And I'm choosing an assortment that maximizes the net expected revenue. And the assortment that I choose always has to be a subset of the products for which I have inventories. Remember, NX was the subset of products for which I have inventories, given that my inventory vector is X. So this is the kind of policy that one derives out of this deterministic linear programming approximation. And it's all based on using the dual variables of the capacity constraints to extract the bid price for each product type. So this is the form of the policy.
Okay. Can I ask you a question?
So then, let me say one last sentence.
Yep.
So then when you think about these bid prices, mu I is characterizing the value of 1 unit of product type. Well, if it's characterizing the value of value I can extract from a unit of product type, mu I should depend on the bid price of a product I should depend on how much time I have left in the selling horizon. If I have little amount of time left in the selling horizon, the value I extract from that product should not be that high. If I have a lot of time left in the selling horizon, the value I can extract from a from a unit of product should be high. So then bid prices conceptually should be time dependent, but the bid prices that we read from the linear program are not time dependent. So what we're going to be able to do is we're going to be able to give an algorithm that constructs time dependent bid prices, and we're going to be able to prove an approximation guarantee for that algorithm. And likewise, these bid prices are characterizing the value of unit of inventory for product I. As such, the value of unit of product I, should depend on how abundant product I is. If I have a lot of inventory for product I, then the value of an incremental unit of product I should not be that much. So then the value of unit of product I should also be capacity dependent as well. And then later on the talk, we're also going to look at capacity-dependent bit prices as well. It turns out that by constructing time and capacity-dependent bit prices, we're going to be able to construct policies that have performance guarantees. Great. So sorry, let me stop here and let me take the questions here. So this is a good pause point for me.
You answered my question, so thank you.
Okay, good, great. Okay, so this is our deterministic linear program. This is how we extract crude bit prices out of this deterministic linear program. And the whole idea of the lecture is going to be, let's try to get more sophisticated bit prices that are time, and also time and capacity dependent bit prices. And hopefully we're going to get policies with performance guarantees out of those bit prices. So that's where we're headed in this lecture. And throughout this lecture, we're not going to make any assumption on the choice model that drives these choice probabilities, right? So in the last lecture, we talked about Markov chain choice model. These choice probabilities could be driven by the Markov chain choice model. In the previous one, we talked about the multinomial logit model and the nested logit model. These choice probabilities can be driven by the multinomial logit nested logit model. So these choice probabilities can be driven by essentially any choice model. So in this talk, we're not going to mold ourselves into a specific choice model that drives these choice probabilities. They can be driven by essentially any choice model. But we're going to put one assumption on the choice probabilities, on the choice model we're going to use. We're going to put only one assumption, and that this assumption is pretty soft. Here's the assumption we're going to use. Remember, PIT of S was the probability that a customer arriving at time period T purchase product I, given that we offer the assortment S. This was the choice probability of product I, given that we offer the assortment S at time period T. We're going to assume that these choice probabilities are coming out of a choice model that satisfies the following property. Let's say instead of offering assortment S, we offer a smaller assortment Q. Instead of offering assortment S, we offer a smaller assortment Q. Then we're going to assume that if you offer us, instead of offering assortment S, we offer a smaller assortment Q, then the choice probability of every product is going to get larger. So if you switch to a smaller assortment, then the choice probability of every product that you're offering is going to get larger. Okay. So it's a pretty harmless assumption. You can prove that any choice model that is driven by the random utility maximization principle that we talked about in the first lecture satisfies this assumption. So all these generalized extreme value models, obviously as a result of that, all the multinomial logit model, nested logit model, and the Markov chain choice model, they all satisfy that property. Okay, so this is going to be one small assumption we're going to be posing in the choice probabilities, which is that instead of offering a large assortment, if I switch to a smaller assortment, then the choice probability of everything that I'm offering is going to get larger. Okay, so that's the assumption that we're going to use. And what is an important implication of this assumption? So here is the important implication of this assumption. Let's imagine that I'm solving an optimization problem that maximizes the net expected revenue. Okay, I'm finding an assortment that maximizes the net expected revenue. Under this assumption, we're going to be able to argue that if A hat T is the optimal solution to this problem, then this optimal assortment never includes a product with a negative revenue contribution. Why is that? If the optimal solution to this problem includes a product with a negative net expected revenue, then I can drop all of the products with negative expected revenues. The choice probabilities of the remaining products are going to increase, and they are all making positive contribution. And I got rid of some products who's making negative expected revenue, who's giving me negative net expected revenue, they were hurting me. So as a result, we can argue that if this assumption holds, in the optimal solution to this problem, I can always drop the products that are making negative net expected revenue contributions to get an even better solution. So as a byproduct of this assumption, we get this result that an optimal solution to this kind of an assortment optimization problem would never include any products whose net expected revenue contribution is negative. So that is going to be the important implication of this assumption that we're going to use throughout the talk. Okay, here's another quick pause point for us. Any questions about this assumption or any questions about its implication? Okay, so again, throughout the talk, we're going to solve these kinds of assortment optimization problems where we're choosing an assortment that maximizes the net expected profit contribution, net expected revenue contributions from the products that we offer. And this is the net revenue contribution of product I. Because of this assumption, An optimal solution to this problem would never include a product whose net revenue contribution is negative. Why is that? If the optimal solution to this problem ever included a product whose net revenue contribution is negative or zero, I can drop all of these products from the optimal solution. So I get rid of all these products who are making me negative or zero net revenue contribution. And also the remaining products are now all making positive net revenue contribution, and their choice probabilities are going to get larger as well because of our assumption. So then I would obtain an even better assortment. Okay. Again, this implication is going to be useful throughout the rest of the talk. So now let's go ahead and try to come up with an algorithm, an idea that's going to allow us to compute time-dependent bid prices. And then by using those time-dependent bid prices, we're going to construct a policy that is going to be guaranteed to get at least half of the optimal expected revenue. So that's going to be a half approximate policy. So now again, let's talk about how we can construct time-dependent bid prices. Okay. So on this slide, we're going to give an algorithm to compute time-dependent bid prices. And as far as this lecture goes, this is going to be the most important slide. So I want to make sure that everybody gets the idea behind this slide. If you can get the idea behind this slide, everything is going to be peanuts. So this is going to be the most important lecture in this slide. So we're trying to compute time-dependent bid prices. And in this slide, we're going to ask two related questions, and we're going to give answers to two related questions. Question number one. Assume that somebody gives us a good assortment, a good subset of products A hat T to offer at each time period T. So let's assume that somebody gives us a good assortment of products A hat T to offer at each time period T. And the question we're asking is, how can I compute the bid price for each product I at each time period T? How can I measure the value of one unit of product I for each product I for each time period T? So that's the first question we're asking. Somebody gives me a good assortment to offer A hat T at each time period T. How can I compute the value of a unit of each product I at time period T? So that's the first question, okay? And let me start with a cartoon here. And then we're going to write that cartoon in mathematical notation. Okay, here's my cartoon. I have CI units of product I. Here they are. Let's focus on one of those units right there. I have CI units of product I. Let's focus on one of those units. And I'm trying to compute the value from one unit of product I. So here is the elementary school computation. Here's the cartoon computation that I'm going to do. At time period T, I'm going to offer my good assortment. I'm going to offer my ideal assortment, A hat T. If I offer my ideal assortment A hat T, this is the probability that a customer is going to purchase product I. If the customer purchases product I, I'm going to route that customer with equal probability to each one of the CI units that I have for product I. So these going to be I'm going to route the customer to each one of the units for product I with equal probabilities. So each one of these probabilities is going to be 1 over CI. And if the customer hits the unit that I'm interested in, then I'm going to make a value of RI from that unit. If the customer does not hit the unit that I'm not interested in, then that unit is going to be available at the next time period. Okay. So this is a super cartoonish, super elementary school way of doing an accounting. And let me repeat my cartoon accounting, and we're going to write that accounting in mathematical notation in a second. So again, I'm sitting at time period T, and I'm trying to compute the value of one unit of product I available at time period T. So I have CI units of product I, and I'm just focusing on one of these units, and I'm trying to compute the value that I can extract from one of these units, okay, at time period T. I'm offering my good assortment, ideal assortment that I was given, A hat T. If I offer my good assortment, this is the probability that a customer purchases product I. If the customer purchases product I, I'm going to route this customer with equal probability to each one of the CI units that I have for product I. If the customer hits the unit that I'm interested in, then I'm going to grab a revenue of RI from that unit. If the customer doesn't hit the unit that I'm interested in, then that unit is going to be available at the next time period. So let me take this cartoonish argument and let me write that cartoonish argument in mathematical notation. Let's let VIT be the bid price of product I at time period T. So that's the value that I can extract from one unit of product I at time period T. I'm going to offer my ideal assortment. If I offer my ideal assortment, this is the probability that the customer purchases product I. If the customer goes for product I, I'm going to route this customer to each one of the CI units of product I with equal probabilities. If the customer hits the unit that I'm interested in, I'm going to make a revenue of RI. With this probability, the customer either doesn't make a purchase for product I or doesn't hit the unit that I'm interested in. In that case, that unit that I'm interested in is still going to be available at the next time period. That is going to be the value for that unit that is available at the next time period. This is kind of like a single unit dynamic program that I'm going to use to compute the bid price for each product I at each time period. So this was our first question, and this is our first answer. If you give me a good subset of products, a good assortment to offer A hat T at each time period T, how can I compute the value that I can derive from each unit of product I at time period T? And this is the computation we're going to make. Okay, the first question, the first answer. Let's ask our second question. The second question is going to be the converse. Let's assume that somebody gives me a good bid price VIT, somebody gives me a good bid price VIT for each product I for each time period T. So somebody gives me the value for each unit of product I for each time period T. And the question is, how do I compute a good assortment to offer at each time period T? How do I compute my ideal assortment for each time period T? Here's what we do. At time period T, if I sell a unit of product I, I'm going to make a revenue for I. But if I sell a unit of product I, that unit is not going to be available at the next time period anymore. And this is going to be the value of the unit that I just lost. So this is the net revenue contribution that I make if I sell a unit of product I at time period T. Well, if I offer the assortment S, this is the probability that a customer is going to purchase product I at time period T at overall products. So this is the net expected revenue contribution that I obtain if I offer the assortment S of products. So my ideal assortment, my good assortment is the assortment that maximizes the net expected revenue contribution at time period T. Okay, so then here's our second question that asks, if you give me the good bid price, if you give me a value of each unit of product I at each time period T, how can I compute a good assortment offer at each time period T? Offer the assortment that maximizes the net expected revenue contribution. Okay, so then the first question, first answer, second question, second answer. The first question was asking, if you give me an ideal assortment to offer at each time period T, A hat T, how could I compute the value of each unit of product I at each time period T? Here's how we're going to do it. The second question asks, if you give me the value of each unit of product I at each time period T, how do I compute a good assortment to offer at each time period T? That's the answer to that second question, offer an assortment that maximizes the net expected revenue contribution. Okay, so these are two questions that we asked, and these are the questions that we answered. It looks like these two questions have kind of a circular logic. In order to answer one question, I'm using the answer of the other question. But it turns out not. We're going to be able to untangle the circular logic. And here's how we're going to do this. We're going to compute these ideal assortments and the bid prices starting from the last time period and moving backwards over time. So here's how we're going to do it. Let's start at the last time period. After the last time period, the bid price of a unit of inventory for each product is going to be 0. I cannot get any money out of these products. So after the last time period, the bid prices are 0. So let's start with the last time period. So if I'm sitting at the last time period, capital T, after the last time period, those bid prices are 0. So if I'm sitting at the last time period, I can solve this problem to compute my ideal assortment at the last time period. Once I computed my ideal assortment at the last time period, I know this assortment. After the last time period, the bid prices are 0. So then once I compute my ideal assortment at the last time period, I know this ideal assortment at the last time period. And after the last time period, bid prices are 0. So I can compute my bid prices at the last time period. So now we move one period back. So now I have my bid prices at the last time period and the ideal assortment. Let's go to time period T-1. At time period T-1, I already have the time periods at the last time period. So I can solve this problem to compute my ideal assortment at the last time period. So now I have my ideal assortment at the second to last time period. I also have my bid price at the last time period. So now I can compute my bid price at the second to last time period. So then by starting from the last time period and peeling these computations back, we can compute the ideal assortment offer at each time period and the bid prices for each unit of product I for each time period as well. So it looked like in the previous slide, our answers were following a circular logic, but it turns out not. By moving over the time periods in the reverse fashion, we can compute the bid price for each unit of product I for each time period T. So this gives us a complete algorithm to compute these bid prices. So it's going to be the bid price for each unit of product I for each time period T. Okay, so let me stop here and let me see if there are any questions about this algorithm to compute bid prices. Again, I motivated this algorithm by a super cartoon picture. Don't take that cartoon picture too literally. It was just to motivate this computation. In a minute, we're going to see that if I use these bid prices, I'm going to get a health approximate policy. So that's why we're ahead. But for the time being, let me take a breather. Again, let me see if there are any questions.
Sorry, one question about the definition of bit prices that you had. That was like some sort of a heuristic and not like the exact counterfactual, right?
Exactly. So for example, the picture that I painted over here is a completely cartoonish picture. So it's I'm only using this picture and I'm only using this English description just to motivate this equation. But later on, we're going to see that, not later on, in 5 minutes, we're going to see that if I construct the bit price policy by using these bit prices, it is going to be good enough to collect at least 50% of the optimal total expected revenue. So these bit prices are going to be good enough to get a performance guarantee, but it's very hard to put a literal meaning on this computation, mathematically precise meaning on this computation. But in a minute, we're going to see that this is good enough to construct a policy with 50% approximation guarantee. Okay?
I see. Thank you.
Yeah, so don't take this like this cartoon at the bottom of the picture too literally. Great. Okay. But I hope that the mechanics of how we do these computations of VIT and the ideal assortment is clear, and that's important for us. Good. Any other questions?
Did you rely on the assumption that the net revenue from a product is non-negative, or this is going to come up in the approximation in the proof of the approximation?
That's precisely what I was going to do next, just the very next step,
okay.
Literally. Okay, good. Any other questions? Good. So again, this is our algorithm for computing our bit prices, and this is how we compute our ideal assortments. Okay. So one of the nice byproducts of this way of computing the bit prices is that, remember, this is the value of unit of inventory for product A at time period T. This is the value of unit of inventory for product A at time period T plus 1. The value of unit of product A at time period T should be larger than the value of unit of product A at time T plus 1, because as we said, if you give me the value, if you give me the unit earlier, I should be able to extract more money from that unit. It turns out these bit prices that we computed satisfies those properties. And here's how. Here's how. Let me write this recursion for VITs in a slightly different fashion. Here's how I'm going to write. That is choice probability times 1 over CI times RI minus choice probability times 1 over CI V at the next time period. So if you collect these two terms together, that's what we obtain. And in that case, I have a 1 times the bit price at the next time period. There's that. So this is this expression is exactly this expression, just a term shuffled around. Okay. So from the assumption that we talked about earlier in the lecture, the choice probabilities get larger when we offer a smaller assortment. We saw that in an optimal solution to this problem, we would never include a product whose net revenue contribution is negative. So that in an optimal solution to this problem in A hat T, we would never include a product for which this net revenue contribution is negative. So if product I is in the assortment A hat T, this net revenue contribution is never negative. So then this term is always a non-negative term. This term is always a non-negative term. That means that VIT is obtained by adding a non-negative term on VIT plus 1. That means that the bit price that we compute at time period T for product I is going to be larger than the bit price that we compute for the same product at the next time period. So because of this assumption, we got this nice intuitive property for our time-dependent bit prices, which says if you give me the product I at time period T versus time period T plus 1, at time period T, I'm going to be able to extract larger value for the product. Okay, so we got this nice side benefit. So as a result of that, what I have is this monotone decreasing property. The bit price of the product at the first time period is going to be larger than the second time period, than the third time period, and all the way to the end. So for a certain product, the bit prices are going to decrease over time. This is not a nice intuitive property. That's not a nice to have kind of a property. But when we do our proofs in a moment, we're actually going to be very dependent on the fact that the bit price for a certain product is going to be decreasing over time. So we're going to use that property in a moment. Okay, good. So then let's go ahead and prove that. Let's go ahead and construct a policy based on these time-dependent bit prices, and now prove that that policy is giving us 50% approximation guarantee. If I move too fast, I don't know why. Okay. let's go ahead and construct a policy by using our time-dependent bit prices, and now we're going to prove that our policy is going to be half approximate. Here's our policy. Here's our approximate policy that's based on these time-dependent bit prices. Here's what we're going to do. Let's say we're at time period t, and the remaining capacities of our product is given by this vector x. Here's what our approximate policy is going to do. Well, if I sell unit of product I, I'm going to make a revenue of Ri. But if I sell unit of product I, I'm going to lose that unit. That unit is not going to be available at the next time period. And here's the bit price. Here's the value of the unit that I'm just going to lose. That's not going to be available at the next time period. So this difference is the net revenue contribution from product I, from the unit of product I that I sell at time period t. Well, if I offer the assortment S at the current time period, this is the probability that the customer is going to go for product I at time period t. So at overall products, this is the net expected revenue contribution if I offer the assortment S at time period t. So in my approximate policy, I'm going to find an assortment that maximizes the net expected revenue contribution at time period t. But of course, the policy that I follow should always be feasible according to my inventories. So the assortment that I offer always has to be a subset of the products for which I have inventories. So this is my approximate policy. That is all there is to it. Let's repeat again. If I'm sitting at time period t, and the remaining capacity of my products is given by the vector x, here's how my approximate policy is going to make its decisions. If I sell unit of product at time period t, this is the revenue I make, and this is the value of the product that I just lose. That product is not going to be available at the next time period anymore. So then this difference is then the net revenue contribution from selling product I at time period t. If I offer the assortment S at time period t, this is the probability that the customer is going to go for product I. At overall products, so this is the net expected revenue contribution I get if I offer the assortment S at time period t. So in my approximate policy, I'm going to find an assortment that maximizes the net expected revenue contribution. And of course, the assortment that I offer has to be a subset of the products for which I have inventories. I cannot offer an assortment that includes a product that I don't have the inventory. So that's our policy, okay? And S at T of X is the assortment that my approximate policy offer, given that I'm at time period T, and the remaining capacities of my product size is the vector X. So that's my policy. And we're going to show that this policy is guaranteed to obtain at least 50% of the optimal expected revenue. Okay, so that's where we're headed. Good, good. So that's what we're going to do. Okay, so here's how we're going to do that. We're going to prove two inequalities. Inequality number one, inequality number two. The first inequality is going to say the following. Let's say we're sitting at time period t and remaining inventories is x. So then we're going to be able to show that the total expected revenue collected by our approximate policy, starting at time period t with the inventories x, is at least as large as this linear function of the inventories. What is this linear function of the inventories? I have xi units of inventory. This is the value of one unit of product I at time period t according to my bid prices. So this is the total valuation of my inventories according to my bid prices. So the first inequality we're showing is saying the following. If I'm sitting at time period t with the remaining inventories x, then the total expected revenue collected by my approximate policy, starting from time period t with the inventories x, is at least as large as the valuation of those inventories according to my bid prices. So that's the first inequality we're going to prove. In a sense, our bid prices are kind of like the pessimistic evaluation of the inventories. Okay, so that is the first inequality we're going to prove. And the second inequality we're going to prove is that this is the evaluation of my initial inventories according to my bid prices at the beginning of the selling horizon. That's the evaluation of my initial inventories. The second inequality we're going to show is that 2 times the evaluation of my initial inventories according to my bid prices, 2 times the evaluation of the initial inventories according to my bid prices is at least as large as the total expected revenue from the optimal policy. So then here's what we get. From the first inequality, if you use the first inequality at the first time period with the initial inventories, this is going to be the total expected revenue collected by the approximate policy, starting from the first time period with the initial inventories. So that is the total expected revenue for the approximate policy. So I'm using this first inequality with the initial inventories at the first time period. So that's going to be, this is going to be the total expected revenue from my approximate policy. While the right-hand side is going to be compute that right-hand side at the initial inventories at the first time period. So that's what the first inequality gives me if I use the first inequality at the first time period with the initial inventory C. On the other hand, I know that this quantity is at least half of the optimal total expected revenue. So then we're immediately going to get the total expected revenue collected by our approximate policy is going to be at least half of the optimal total expected revenue. Okay, so these are the two inequalities that we need to establish, and that's what we're going to do next. Okay, so let me take a pause here. Any questions about these two inequalities? Any questions about where we're headed in order to accomplish, in order to get the proof that our approximate policy is giving us half of the optimal total expected revenue? Any questions? Good. So now let's show the first inequality. What we want to show is that the total expected revenue collected by our approximate policy, starting from time period t with the capacities x, is at least as large as this linear function of the inventories x. So that's what we want to show. So in order to do that, let me first write a dynamic program that computes the total expected revenue collected by our approximate policy. Okay? So this was the decision function, if you will, for our approximate policy, right? In our approximate policy, if I'm sitting at time period t with the remaining capacities x, then the assortment that my approximate policy offers is given by find an assortment that is capacity feasible, that maximizes this net expected revenue, where the net revenue contribution of product I is given by revenue of product I minus its bid price at the next time period. So this is the decision function of my approximate policy that is telling me the assortment that my approximate policy offers at time period t, given that the capacity is x, given that the capacity is x, and let's use s hat tx to denote the assortment that is offered my approximate policy, given that I'm sitting at time period t and the capacities of my products is given by the vector x. So now let's write a dynamic program that computes the total expected revenue collected by our approximate policy. Here's that dynamic program. Let me let theta hat t of x be the total expected revenue collected by the approximate policy, starting from time period t with the capacities x. This is the total expected revenue of our approximate policy, starting at time period t with the capacities x. Well, according to my approximate policy, if I'm at time period t and the capacity is x, this is the assortment that we offer. If I offer this assortment s hat t of x, this is the probability that the customer goes for product I. If she goes for product I, this is the revenue that I obtain. And this is the total expected revenue collected by my approximate policy, starting from the last time period on, after losing 1 unit for product I. And with this probability, the customer doesn't purchase anything. If the customer doesn't purchase anything, I'm going to walk to the next time period with the same amount of capacity that I had. This is the total expected revenue collected by our approximate policy, starting from the next time period on. So this is the same kind of dynamic program that we formulated when we were trying to compute the optimal expected revenue, but we formulated here considering the fact that the assortment is not subject to optimization anymore. The assortment of our approximate policy is just fixed by the assortment, is just fixed by our approximate policy. I don't need to find an assortment to offer. Okay, so this is the dynamic program that we need to solve to compute the total expected revenue collected by our approximate policy, starting from a certain time period with certain capacities. Let's shuffle the terms in this dynamic program. It's going to be useful for us. Choice probability times the value function at the next time period after losing 1 unit of inventory. Choice probability times the value function at the next time period after losing 1 unit of inventory. I forgot the hat here, so keep that. And likewise, minus the choice probability times the value function at the next time period without losing inventory, minus the choice probability times the value function at the next time period without losing the inventory, and there is 1 times the value function at the next time period. There is that. So these are the two dynamic programs, just the things shuffled around. So what we wanted to show was, remember, the total expected revenue collected by our approximate policy, starting from time period t with the inventories x, is at least as large as this linear function of the inventories. What we want to show is this inequality. The total expected revenue collected by our approximate policy, starting from time period t with these inventories, is at least as large as this linear function of the inventories. So this is the first inequality that we would like to prove. Okay, good. We're going to prove this inequality by using induction over the time periods. Namely, we're going to assume that this inequality holds at time period t plus 1, and then we're going to establish that this inequality holds at time period t as well. So this inequality is going to come from a just brute force induction argument. Okay, so that's what we're going to do. Here we go. This is our good old dynamic programming recursion to compute the total expected revenue collected by our approximate policy. So this is the same dynamic program that we had on the previous slide. Good. So then by my induction assumption, what do we have? Theta at T of X is upper bounding this. I'm sorry, by my induction assumption, what do I have? Theta at the next time period is upper bounding this linear function of the capacities. Okay, so then if I replace all these thetas on the right-hand side by their lower bounds, I'm going to make the right-hand side smaller. So let's replace all these thetas on the right-hand side by their lower bounds. Replace this guy by its lower bound. There it is. If I replace both of these guys by their lower bounds, what do I obtain? Well, this is a linear function of x, all good. This is a linear function of x, the same linear function of x, but I'm losing 1 unit of capacity for the ith product. So if I take this difference, all I'm going to have is this slope for the ith product. So that's what I obtain if I replace both of these two guys by their lower bounds. So as a result, I made the right-hand side even smaller by replacing all of these thetas by their lower bounds. This is coming from the induction argument. Good. Okay. So then what do I have? By the definition of my approximate policy, the approximate policy is obtained by maximizing this objective function. The approximate policy is obtained by maximizing this objective function. So the S at T is nothing more than the optimal solution to this maximization problem. So instead of computing the objective value of this maximization problem at its optimal value, so let me just write the maximization problem in explicit form. Again, this is just coming because of the fact that my approximate assortment, the policy that's coming from my approximate, the assortment that's coming from my approximate policy is the optimal solution to this maximization problem. That is the definition of my approximate policy's assortment. Good. So then this is an equality. Okay. So here is an important thing that's non-trivial. Let's focus on this assortment optimization problem. Okay. In this assortment optimization problem, I can only offer products which they have positive inventories or they have non-zero inventories. So then what I'm going to do is the following. If I want to focus only on products that have positive inventories, what I can do is that I can look at every product and set its revenue contribution to 0 when that product has 0 inventory. So this is the indicator function. So I look at every product and set its revenue contribution to 0 when that product has 0 inventory. Then from the very beginning of the lecture, we know that when I solve an assortment optimization problem like that, if a product has 0 or negative net revenue contribution, we would never include that product in an optimal solution to this kind of an assortment optimization problem. That's coming because of our assumption on the choice probabilities. So then this problem and this problem is perfectly equivalent to each other, because in this problem we say never offer a product for which you don't have the inventory. In this problem you say you can offer any product that you want, but if you offer a product for which you don't have the inventory, you make a 0 revenue contribution. As a result, in an optimal solution to this problem, you would never offer products that have 0 or negative revenue contributions as well. So this problem would also never offer a product with 0 inventory contribution as well. So as a result, this problem would never offer a product for which we do not have inventories. So then these two problems are equivalent to each other. So we're still operating at equality level. So this is one other area where our assumption became useful. So the next thing we're going to pay attention is the following. This is the indicator function. So the indicator function looks like this. Xi is over here. At 0, that indicator function takes value 0. And at 1, 2, 3, that indicator function is going to take value 1. So the indicator function looks like this. So this is the function 1 xi strictly positive. So I'm going to construct the lower bound on that indicator function. And that lower bound is going to be the following. Let me take this line. And the larger value of the capacity for product is Ci. So if I take this line, that is Xi over Ci. So at Ci, it's going to be that green line at Ci, it's going to be exactly equal to 1. This linear function is a lower bound on the indicator function. So let me replace my indicator function by its lower bound, that linear function. So I made the right-hand side even smaller. Okay. Good. let's remember how we computed our ideal assortment. When we were computing, okay. Let's think about when we were computing our ideal assortment. The ideal assortment was the maximization, was the optimal solution to this maximization problem. So the optimal solution to this maximization problem is A hat T. So let's replace that by A hat T. And the last thing we're going to pay attention, sorry. That's not that argument. Sorry, let me take it back. Here's an optimization problem. Instead of computing the objective value of this optimization problem, let's just compute the objective value of this optimization problem at a feasible solution. And A hat T, my ideal assortment, is just one feasible solution. So I made the right-hand side even smaller. Instead of solving this optimization problem, I just computed its objective value at a solution. So I made the right-hand side even smaller. And lastly, let's pay attention to the update formula that we use to compute our bid prices. Let me remind you what that update formula looked like. Let me write it over here. That update formula looked like this. So that was our update formula to compute our bid prices. Good. So then what we're seeing over here is, if I carve this guy out, if I carve this guy out, that is exactly equal to this number. So this number is exactly equal to VIT minus VIT plus 1. So I carve this guy out. That is exactly this term appearing in my update formula. So that's exactly equal to the difference of the bid price at the two time periods. There is difference of the bid price at the two time periods. So that's an exact equality. So then what do I have? This is VIT times XI, VIT plus 1 times XI. I've been carrying out this VIT plus 1 times XI's all through. So then these are going to cancel. So then I have the linear function of the capacity. So from this long argument, what we saw is that the total expected revenue collected by our approximate policy, starting from time period T with the capacities X, is lower bounded by this linear function of the capacities. So this is the first inequality that we wanted to show, and we show that by using induction. Okay, so let me take a stopping point and let me see if anybody has any questions.
Yes, I have a question. I did not understand from the first to the second line, you replaced the theta functions by their lower bounds. But how can this be done if the theta is negative on the left-hand side? Don't we need some concavity property maybe?
Good, great. So I glossed over that intentionally, but let me, now that I've been caught, let me not gloss over it. And the reason we can do that is the following. Let me roll back to the original dynamic program that we have. If you look at the original dynamic program that we have, both thetas are appearing with positive coefficients here. This theta has a positive coefficient. This theta also has a positive coefficient here. This is a positive number. Okay, so then there was, I wanted to fit everything on one page. So if I wrote this thing in a way that these thetas were bracketed together so that this guy and this guy were together, in that case, it would have a coefficient of 1 minus the choice probability. Then that one would have a positive coefficient in front of it. Then this one would have a positive coefficient in front of it. In that case, I would be able to replace them by something smaller. And then I would re-bracket them again to get something like this so that I could take the difference of those two guys and I would get down to VIT plus 1. Good, so you didn't let me get away with it, but now we're all 100%. There's no cheating now.
Thank you.
Good, thanks. Okay, any other comments?
Just a quick one. Like it seems this bound is based on this 1 over CI, kind of like
Yes.
you need for me, you know, like your cartoonish example, I think is quite nice, right? Just the thing that comes to mind, can we do better than this 1 over CI? I mean, probably not, but it's like, can we have a bound that is, you know, non-linear to some extent that can bound this better? Yeah.
So for these kinds of matching problems, you can prove, even in a simpler matching settings, you can prove that in a certain sense, and let me get you to the certain sense after we fully finish the proof, okay? But in a certain sense, you cannot come out with any policy that's going to give you a better than a half guarantee. So I'm not sure whether this argument is tight, but in the end, I know that I cannot give you any policy that is going to give you a better than a half approximation. So in that sense, the policy that I'm giving you is as good as it gets.
Yeah.
So that's that.
Okay.
Okay. For these kinds of matching problems, even in very much simpler settings, you cannot improve these kinds of bounds better than 2.
Right.
So that's what I'm gonna leave it at that. Okay. Any other comments? Okay. So then there are a few tricks that we used here, right? So the first one is, again, we're going to prove this inequality by using induction over the time periods. We start with the dynamic program that computes the total expected revenue from our approximate policy. So then we follow the induction argument by replacing these thetas by their lower bounds, which is these linear functions. So this inequality comes from the induction argument. And the next thing we talked about was the approximate policy is exactly computed by the assortment that's offered by our approximate policy at time period t given the capacity is x is exactly computed by solving this optimization problem. So then this is nothing more than the optimal objective values optimization problem. So then this these two expressions are holding at the equality level. Keep on dragging these things down. Another, the first interesting realization that we made in the proof was the following. Here, I'm trying to find an assortment that is feasible according to my inventories. A good way of finding an assortment that is feasible according to my inventories is to say, in your assortment optimization problem, set the net revenue contribution of every product for which you don't have an inventory to 0. In that case, we know that in this assortment optimization problem, we would never offer a product whose net revenue contribution is 0 or negative. So as a result, we can take this feasibility condition on the assortments that we can offer into the objective function by setting the net revenue contribution of the products with 0 inventories to 0. So then these two things are operating at the equality level. These two things are exactly equal to each other. So that's one cute realization, if you like. The other cute realization was lower bounding this indicator function, which looks like this, by a linear function. So that was the second cute thing that we did. And the rest was kind of mindless. Instead of solving this maximization problem, we computed this objective function at a feasible solution. So as a result, this thing got even smaller. I'm just computing the objective value to max at a feasible solution. So the right-hand side got even smaller. And then we finally realized that this term is appearing in the updates that I use for my bit prices. So this term is nothing more than the difference of the value functions at the two successive time periods. That's what we obtain. And adding this and this gives me the linear function at the next time period. So this is the first inequality that we wanted to show. Okay, so let's go to the second inequality that we wanted to show. We wanted to show was the following: 2 times this initial evaluation of the capacities with the initial bit prices and at the initial capacities is at least as large as the optimal total expected revenue from the optimal policy. Here's how we're going to do that. Remember the deterministic linear program that we looked at the very beginning of the talk? Here is this deterministic linear program. Okay. And it's a very well-known result in the revenue management literature is that if you just read the optimal objective value of this deterministic linear program, it's an upper bound on the optimal total expected revenue. So that is something very well known. The fluid approximation gives us an upper bound on the optimal total expected revenue under the optimal control policy. That is something we're going to leverage on. So the optimal objective value of our linear program is an upper bound on the optimal total expected revenue. So let's put that in our pocket. Okay. So then, instead of solving the primal of the deterministic linear program, let me solve the dual of our deterministic linear program. Let me associate the dual variables mu I and sigma t's with these constraints, and let me write the dual of the deterministic linear program. So in the objective function, we have ci times mu I, 1 times sigma t, add it all up in the objective function. We're minimizing that. And in the constraint, I'm trying to write the constraint that corresponds to the primal decision variable zt of s. In this constraint, the coefficient of zt of s, pit of s. So pit of s times mu I added over all I. In here, the coefficient of zt of s is 1, so plus sigma t. That's greater than or equal to the objective function coefficient of zt of s. What is the objective function coefficient of zt of s? It is this number. There's that. So this is just the dual of the deterministic linear program. So the objective function of this problem is z star as well. Okay. So let me fiddle around with this dual. Let me take this term, throw it to the right-hand side. If I throw this thing to the right-hand side, what do I have? Choice probability times Ri minus mu I. Here is the dual. I didn't do anything. I just threw this term that was on the left-hand side to the right-hand side, so it's the same dual. Good. Let's do something else. In the objective function, I'm minimizing the objective function. So I'm going to push sigma t as low as possible. So if I push sigma t as low as possible, sigma t is going to get stuck at the largest value of this expression over every assortment, because sigma t has to be greater than or equal to this for every assortment. So sigma t is going to get stuck at the maximum value of this expression over every assortment. So at the optimal solution, sigma t is going to be the max of this over every assortment. So I can replace sigma t by max of this over every assortment, plug it into the objective function, and drop this constraint altogether. So here's what I did. Replace sigma t by max of this expression over every assortment, replace sigma t by max of that expression over every assortment, and drop that constraint. So this is the dual of the LP. Just a few iterations we did on the dual of the LP, but this is the exact same dual. And again, since this is the dual of the LP, this thing also has the optimal objective value z star. And remember, we said that z star is an upper bound on opt. Okay, so this is where we stand right now. So here is the important claim that we're going to prove. And that's what we're going to do on the next slide. The important claim we're going to prove is the following. We're going to show that, what are the decision variables here? Mu i's. We're going to show that if I take my bit prices at the first time period, VI1s, we're going to show that if I take my bit price at the first time period, VI1s, those VI1s is a feasible solution to this dual LP. And furthermore, these VIs provide an objective value for this LP that is no less than 2 times this linear function of the initial capacity. So that is the claim we're going to prove. We're going to prove that VI1s is a feasible solution to this dual LP. Okay. And furthermore, these VIs is going to give an objective value for this problem that is less than this number. So then what do I obtain? What we have is the following. Opt upper bounded by z star. So z star is an upper bound on opt. Okay. Z star over here is given by a minimization problem. So then z star is going to be less than the objective value of the dual at the feasible solution VI1s. So this is a minimization problem. Its optimal objective value is going to be smaller than the objective value of this problem at a feasible solution. Good. Z star is going to be less than the objective value of the dual at the feasible solution VI1s. And once we prove this claim, we said that the objective value of this problem evaluated at VI1s is going to be less than this 2 times CI times VI1s added all up. So then what do we obtain? 2 times CI times VI1s, 2 times our initial valuation of the capacities is an upper bound on the optimal total expected revenue. This is exactly the second inequality that we set out to solve. Okay, so that's how we're going to do this. So then there is one last thing that is left to show. We want to show that if I compute the objective function, first of all, I want to show that VI1s overall I is feasible to this dual. Okay, and furthermore, if I compute the objective function of this problem at the VI1s, it's going to be less than 2 times the initial valuation of the capacities. Good. And before we do that computation, any questions about this part of the proof, the second part of the proof? Good. And let's go ahead and do this. Let's go ahead and finish this up. First of all, are these VI1s feasible to this problem? What is the only feasibility constraint that I have on this problem? Mu's should be non-negative. Mu's should be non-negative. And so all I need for VI1s to be is, I want VI1s to be non-negative. But we already shown that these VIs are going to satisfy this monotonicity property. And let me also put the boundary condition of the bid price after the last time period, and that's 0. So by default, all of our bid prices are going to be non-negative by our construction. So these VI1s are indeed feasible to this dual problem. So that all that remains to show is that when I compute the objective function of our dual problem at the VI1s, I'm going to get at most 2 times CI times VI1s. That's all I need to show. The objective value of my dual, evaluate that this feasible solution is going to be less than this 2 times the initial valuation of the capacities. That is all we need to do. So now let's go ahead and compute the objective value of my dual problem at the solution VI1s. Replace this by VI1 and replace this guy by VI1. Mu by VI1, mu by VI1. Here we go. So I replace that mu by VI1, replace mu by VI1. I want to show that that number is less than the 2 times the initial valuation of the capacities according to my bid prices. Great. Okay. So the first one, keep this guy as it is, keep this guy as it is. And we say that our bid prices are decreasing over time. So then instead of using VI1 here, if I use VIT plus 1, this is smaller than that. There is a negative sign in front. So I made this guy larger. So as a result, I have a greater than or equal to sign here. Instead of using the bid price at time period 1, then I'm using the bid price at time period T plus 1 here. So I made the right-hand side smaller. Great. Remember in our construction of the algorithm, when we computed our ideal assortment, what did we say? When you compute your ideal assortment, find an assortment that maximizes this net expected revenue contribution. And the net revenue contribution from product I would be its revenue minus the bid price at the next time period. So this is the problem that we solved to compute our ideal assortment at time period T. This is the problem that we solved to compute our ideal assortment at time period T. So the optimal solution to this problem is our ideal assortment at time period T. So now plug the ideal assortment at time period T. This is the optimal solution to this problem. So I'm still operating at the equality level because this thing is the optimal solution to this problem. That's how I compute my ideal assortment. Good. For the next equality, let's again refer to our bid price update formula. What's our bid price update formula look like? That was the bid price update formula that we constructed from our cartoon. So now what do we have here? If you look at this term over here, it's appearing right over here as well. So this is Ri. So this term over here is appearing right over here as well. So I can write this term as, the bid price at the successive time periods multiplied by Ci. So this term is the same as this guy here. So I can write this term as bid price at the successive time periods multiplied by Ci. There is that. So then this is operating at an equality level because this guy is exactly equal to the bid price at the 2 time periods multiplied by Ci. If I take the sum over every time period, what do I have? First, I'm going to have, let me write it in green here if you like, Ci times Vi1 minus Vi2. That's the first time period component. Keep going. Ci times Vi2 minus Vi3. Ci times Vit minus Vit plus 1. So if you do the sums, these things are going to cancel in a telescopic fashion. After the last time period, the bid prices are 0. So if I take the sum, things are going to cancel in a telescopic fashion. All I'm going to be left is Ci times Vi1. There is that. So I have 1 times Ci times Vi1, 1 times Ci times Vi1. That's going to give me 2 times Ci times Vi1 added over all x. So this is how we get, if I compute the objective function of the dual LP at the initial bid prices, I get at most 2 times the initial evaluation of the inventories. So as a result, optimal objective value of the LP is an upper bound on opt, and that is less than the objective of dual at feasible solution Vi1, and we just show that this is less than Ci times Vi1. So then 2 times our initial evaluation of the capacities at the initial time period with the initial bid prices is at least as large as the optimal total expected revenue. So now I'm putting it all together. We showed this one by using a feasibility argument in the deterministic linear program and using the fact that deterministic linear program gives me an upper bound on the optimal total expected revenue. We showed this one by backward induction over the time periods, and then that gives us the total expected revenue for our approximate policy, at least half of the optimal total expected revenue. Good. Let me stop here. Any questions about the proof? It's the kind of proof that I can show you in 20 minutes. It's just chasing down inequality, so there's not too much intelligence in it. Okay, any comments, any questions? Okay. So that's where we left. So when we first got this, we were pretty happy. Oh, it's a very nice two approximation for the, it's a nice two approximation. But one of the undesirable things, there is actually an undesirable thing about this policy, and it's the following. In our approximate policy, this is the optimization problem that we solve to compute the assortment offer, given that we're sitting at time period t and the remaining capacity is x, right? So if you look at the capacities of the products only play a role on deciding whether a certain product is feasible to offer or not. Namely, if a product has 1 unit of capacity versus a product has 1 million units of capacity, that product is still feasible to offer, then you do not differentiate between those two cases. So in a sense, the policy that I constructed here is agnostic to the inventory availabilities. If I'm sitting at the same time period with 1 unit of inventory available for a certain product versus 1,000 units of inventory available for a certain product, that product is still going to be feasible to offer. As a result, this policy is not going to distinguish between those two cases. So good, it gives you a half approximation, but this policy is inventory agnostic. So now we're going to go ahead and construct not only time, but also capacity dependent bid prices. And that policy hopefully is going to be a policy that is not going to be as agnostic to the inventory levels. And that policy is also going to get a half approximation guarantee. Good. Here's the same kind of slide we're going to look at. We're going to ask 2 questions on the slide, 2 related questions, and we're going to answer to those 2 related questions. Question number 1. Question number 1. Let's say that I have a good ideal assortment to offer A hat T at each time period T. So somebody gives me a good subset of products, good assortment A hat T to offer at each time period T. Then the question I'm asking is, how do I measure the value of having xi units of product I at each time period T? So you give me a good assortment A hat T to offer at each time period T. How can I measure the value of having xi units of product I at each time period T? Here's how we're going to do that. This is the value of having xi units of product I at time period T. So this is the value of having xi units of product I at time period T. Well, here's what I'm going to do. I'm going to offer my good assortment, my ideal assortment. If I offer my good assortment, this is the probability that a customer is going to go for product I. If the customer goes for product I, and if I still have inventory for product I, I'm going to make a revenue from product I, or I. Then I'm going to walk into the next time period with 1 less unit of inventory for product I. And it's the value that I drive from xi minus 1 units of inventory for product I starting at the next time period. With this probability, if I offer my ideal assortment, the customer either does not choose product I or the product has 0 inventory. In that case, I'm still going to walk into the next time period with the same amount of inventory that I have for product I. So this was our first question and our first answer. Give me an ideal assortment to offer at each time period T. How do I measure the value of having xi units of product I at each time period T? This is the recursion that we're going to solve. And this is essentially a single dimensional dynamic program, right? Xi is a function that has got a scalar argument to it. So I can compute these UITs for every value of xi by moving backwards over time, if you like. Okay, so that's our first question and our first answer. The second question is the kind of the reverse question. How do I compute a good subset of products to offer at each time period T? And the answer to this question is that just find an assortment that maximizes the net expected revenue contribution. But here I'm going to continue using my time-dependent, but not capacity-dependent bid prices. So I'm going to continue using my time-dependent bid prices to compute my ideal assortments. Okay. So again, that's my second question, and that's my second answer. Question number 1, if you give me a good assortment to offer at each time period T, how do I measure the value of having xi units of product I at each time period T? Here's the answer. Question number 2, how do I compute a good assortment to offer at each time period T? That's the same as before. find the assortment that maximizes the net expected revenue contribution. And again, net revenue of each product is computed by using the time, but not capacity dependent bid price of the products. Okay. So then how do I compute these UIs and the ideal assortments? We're again going to walk backwards over time. After the last time period, all the time-dependent bid prices are 0. After the last time period, all the capacity-dependent bid prices are 0. Then starting at the last time period, time period capital T, this is 0. So I can solve this problem to compute my ideal assortment. After the last time period, these are all 0. I know my ideal assortment at the last time period. I can compute my time-dependent bid price at the last time period. So then let's keep on moving backwards. At the last time period, I know my ideal assortment at the last time period. After the last time period, these bid prices are 0. So then I can compute my UIT for every value of xi to compute my capacity-dependent bid prices. So I got all of these things done. We move one time periods back. I'm sitting time period T minus 1. I know my time-dependent bid prices at the last time period. So at time T minus 1, I know the time-dependent bid price at the last time period. So compute your ideal assortment at time period T minus 1, and then you keep on walking backwards to compute all these time and capacity-dependent bid prices hand in hand. So once we compute these capacity-dependent bid prices, what is our approximate policy going to look like? I'm sitting at time period T, and the remaining capacities on my product is given by my vector X. So what is my approximate policy going to do? At time period T, if I sell a unit of product I, this is the revenue I make. But at time period T, if I sell a unit of product I, instead of having xi units at the next time period, I'm going to have xi minus 1 units. So this difference is the value of the unit that I just lost by selling 1 unit of product I at time period T. So then this difference is the net revenue contribution from selling units of product I at time period T. Just the bid price is computed by using the capacity-dependent bid prices. And I'm finding an assortment that maximizes the net expected revenue contribution. But of course, I'm making sure that the assortment that I offer is a subset of the products for which I have inventories. It turns out that this policy is also going to get at least half of the optimal total expected revenue. Okay. So I'm going to show you a very high level of the idea behind the proof of this result as well. Before I do that, let me roll back 2 slides and let me try to clarify why I chose time-dependent bid prices, but not the capacity-dependent bid prices to compute my ideal assortment. Why did I not do something even better, plug in my time-dependent bid prices over here? And the reason for that is the following. If I plugged in the capacity-dependent bid price on the right-hand side, namely replace this guy by this value of unit of inventory, so then this A hat T would depend on, look, when I compute this A hat T, I look at all the products together. So then this A hat T would be jointly depending on the inventories of all of the products. So then this would be an assortment that I would not be able to keep track of in my computer in a tractable fashion, because it would again jointly depend on how many units of inventory that I have for all of the products. So this thing would be dependent on the inventory of all of the products. So this would be a number that I would not be able to store in my computer in a tractable fashion. This would be almost as difficult as solving the original dynamic program. That is why we opted for the time-dependent bid price over here when we compute our ideal assortments. Okay, so let me just clarify if anybody was having any hesitations about that. Good. So again, this is how we're going to do it. We're going to compute our ideal assortments, time-dependent, and time and capacity-dependent bid prices hand in hand by moving backwards over time. I need to compute my time-dependent bid prices because I need them to compute my ideal assortments at every time period. But once I compute my capacity-dependent bid prices, I don't know why I go too fast like this. Once I compute my capacity-dependent bid prices, this is the form of the policy that we're going to use for these capacity-dependent bid prices. Good. Let me take another breather. Okay. How does the 50% approximation guarantee for this more sophisticated capacity-dependent bid price policy going to look like? It's roughly the same idea. We proved 2 inequalities. Here's how those 2 inequalities look like. The first one says the following: the total expected revenue collected by our approximate policy, starting from time period T, with these initial inventories, is at least as large as the evaluation of those inventories according to our capacity-dependent bid prices. Now, this again, you can show this by using backward induction over the time periods. And I'm not going to show that, but you can show that by using backward induction over the time periods. The second thing that we can show is that the valuation of our inventories according to our capacity-dependent bid prices is at least as large as the valuation according to just time-dependent bid prices. You can again show this by using induction over the time periods as well. So these are the two inequalities that we need to show to get the performance guarantee. One is the total expected revenue collected by our approximate policy, starting from time period T with the inventories X, is at least as large as the valuation of those inventories according to our capacity-dependent bid prices. And the valuation of the inventories according to our capacity-dependent bid prices is at least as large as the valuation according to time-dependent bid prices. Both of these you can establish by using backwards induction over the time periods. So then if I compute the first inequality at the first time period at the initial inventories, this reads total expected revenue of the approximate policy. Total expected revenue of the approximate policy. So I'm computing the first inequality at the first time period at the initial inventories. That is lower bounded by the valuation of the initial inventories according to our capacity-dependent bid prices. But we know that these guys are lower bounded by the valuations according to the time-dependent bid prices. That's the second inequality. And from the first part of the talk, we know that that is at least opt over 2. That is something we showed step by step in the first part of the talk. Okay. So then putting all these things together, the total expected revenue from our approximate policy with the capacity-dependent bid prices is at least half of the optimal total expected revenue. Okay, good. So then we have these policies. Let me go over a few numerical results really fast, but I'm not going to spend too much time on the numerical results. So we have some experiments on a problem with 3 parallel flight legs, and this data set is taken from a paper by Gerrit van Rysden and Qian Liu. But what we obtain is the following. Let me show you the numbers at a very high level. We have 9 different test problems here. And the blue bar corresponds to the total expected revenue collected by our time-dependent bid prices. The red bar, correspond to the total expected revenue collected by our time-dependent bid prices, red bar. The blue bar is the total expected revenue collected by our capacity-dependent bid prices. So as you see, blue bar is always larger than the red bar. So these sophisticated capacity-dependent bid prices actually buy something, improves the revenues. And this green bar is the performance of the policy that use the bid prices from the deterministic linear program. So sometimes the green bar is worse than the red bar, worse than the red bar, worse than the red bar. But sometimes the green bar can be larger than the red bar. So sometimes the bid price from the deterministic LP is better than our time-dependent bid prices, but at least our time-dependent bid price has 50% performance guarantee. But the nice thing is our blue bars are always better than the red bar. So our capacity-dependent bid prices are always doing better than the bid prices coming from the linear program. And let me not talk about the yellow bar here right now. Okay, so let's wrap this up. So now I give you a problem that takes place over time. And if you look at its dynamic programming formulation, it's not a dynamic program that we can tractably solve, but it turns out that it's not too hard to design half approximation guarantees for these kinds of problems. And going back to Victor's question along the way, I said that it's not possible to get better than half approximation guarantee for these problems. Let me try to qualify this statement. When we were trying to get our approximation guarantee, we were comparing our performance of the policy with the deterministic linear program's upper bounds. So as long as you compare yourself with the deterministic linear program's upper bounds, you can show that you'll never be able to get better than half approximation, okay? But if you compare yourself with a better benchmark, maybe you'll be able to get something better. But as long as you compare yourself with that, with the deterministic linear program, which is an upper bound already, you'll never be able to get better than the half of the deterministic linear program. Okay, so some extensions. So I gave you a class of bid prices that gives us half approximations, but it turns out that there is a paper that uses directly the deterministic linear program to give yet another half approximate policy. And I'm going to give that paper in my references. So you can actually leverage the LP as it is to get yourself another half approximate policy. And there's a reference for that I'm going to give you. You can extend everything that we talked about today to reusable products. And what I mean by reusable products is that a customer chooses a product, uses that product for a certain duration of time, and returns the product back into the system. So you can use the same kinds of arguments when products are reusable. So you can model things like rent the runway, where people are renting dresses and different kinds of clothing equipment. After they use the clothing equipment, they return it back to you, and they choose among the assortments of clothing equipment that you offer to them. When products are reusable, this also works out. This is an extension that I'm quite happy with it. You can extend all these ideas to the network case. Here, if a customer purchased a product, you only consume the inventory of that product. But these ideas extend to the network revenue management case as well. When a customer purchases a product, he consumes multiple resources. He consumes the inventory of multiple resources. Now we can prove that if each product uses at most L resources, then we can give you a 1/1 plus L approximate policy. In our problem, each product exactly used one resource, which is the inventory of itself. So L was 1, we got a half approximate policy, but we can extend these results to the case where each product uses at most L resources. In that case, we can give you a 1/1 plus L approximate policy. So these ideas generalize to network revenue management problems. And as far as I know, this is the only constant factor approximation policy for network revenue management problems when you do not go into asymptotic regimes or anything like that. So this doesn't require an asymptotic regime. And lastly, our assortment optimization problem was dynamic here. So namely, we could change the assortment for every individual arriving customer. There is another class of assortment optimization problems where initially we set the inventories of the products, and then the assortment that the customer sees is the assortment of products that are left on the shelf. The assortment that the customer sees is the assortment for which we have positive inventories. You don't do any active assortment control ever. Your only decision variable is which inventories you stock at the beginning of your selling horizon. Those problems are much, much harder than the class of problems that I looked at here, that we looked at here. So when you just initially stock the assortments, and then the assortment that the customer sees is the products for which we have inventories, the problem becomes much harder. I'm going to give you some references for that as well, but those problems are, I cannot give you an approximation guarantee for them on 3 slides. Okay, so let me wrap up with some references. So the ideas that we talked about in this talk is coming from this paper, and the generalizations to network revenue management problem are in this paper. The policy that I said that you immediately grab from the deterministic linear program and that you can still show it's half approximate, it's coming from this paper. It's a paper that is to appear in Management Science, a relatively recent paper. And all of the ideas that I showed you to get these approximation guarantees goes to an earlier paper by these 3 colleagues at Columbia University. So if you look at these 2 papers, and if you read this paper carefully, you're going to see a lot of analogies between all of these 3 papers. These 2 papers do the problem where you initially set the inventories for the products and do not touch your assortment. The assortment that the customer sees is only the products that's available on the assortment. So you cannot decide, I'm not going to show this product to a customer. Actually, these 3 papers look at that kind of a problem setting, and the problems are a lot more difficult in that setting. Actually, let me roll back. These 3 papers are in that setting. This is another paper that looks at reusable products, reusable resources, that was sort of concurrent with our work. And there are a few other papers that look at the deterministic linear programming formulations to get policies with performance guarantees. Here is one of those papers. And with that, I mentioned Aydın's work here, and I did not give you a specific reference. Aydın's work for the exponomial model that we talked about at the end of the very last lecture. Here is the specific reference for Aydın's work. And with that, I'm going to stop. Maybe we can take another question or 2. But this is all I had to say for my sequence of 3 lectures. So we start with this dynamic assortment optimization setting.
Any question, guys, before we close? Thank you so much anyway. Any question? No.
Great. Thank you all. And we post the slides on the course website.
Thank you so much, Huseyin. Thank
My
you.
pleasure, my pleasure. And thanks everybody for making the time again. It's an unreal amount of time.
It's
Thank you.
really cool. Thank you so much. Have a great day at your end, and I hope to see you all guys on Wednesday.
Thank you again. Thanks everybody also for putting in the chat. Thank you. Much appreciated. Thanks, guys.
Thank you.